Irrigation is widespread across the lower Arikaree Basin, with wells pumping from both the deep regional aquifer as well as from the shallow alluvial aquifer through which the river flows. We chose to model the dynamics of groundwater and aquatic habitats in the upper portion of this region for two reasons. One, this is where the regional aquifer feeds the alluvium. All surface flow originates in this area. And two, this is where the best habitats for fishes remain. Our objective for this research was simple: to predict how long into the future habitats for fishes will remain in the Arikaree under different scenarios of pumping. Our goal was to make recommendations where habitats will persist above a threshold in conservation, allowing populations to remain viable, and not to continue on a trajectory towards extinction. First, we needed to make the link between groundwater levels and fish habitats. We drilled wells and monitored groundwater levels throughout the spring, summer, and fall of 2007, and measured the depth of pools in the river during the same time period. We found that the depth of fish habitats in the river was a direct reflection of water table levels through the growing season. As a result, we were able to predict the depth of pools into the future with our groundwater model, based on water table level changes over time. Our groundwater model was based on the flow of ground and surface water into and out of the regional and alluvial aquifers. The model output was the change in water table level over time. Based on this output, we calculated the percentage of pool habitats remaining along one 4-mile river segment after 40 years under the following three scenarios. The first scenario was to keep the status quo, to continue pumping at current rates from the current number of wells. The second scenario was to remove wells pumping from the alluvial aquifer. We chose this scenario because the alluvial wells likely have a disproportionate impact on surface flows. We observed that stream reaches that are adjacent to irrigated fields are dry by late summer. This is because alluvial wells cause a cone of depression in the water table that intersects the river. Essentially, these wells are intercepting surface and subsurface flow from upstream. Our third scenario was to turn off all wells within a 3-mile band around the river. This scenario was consistent with a proposed management plan from the Colorado State Engineer's Office. Here are the results of our models, as the percentage of fish habitats remaining over time. Overall, we found that water table levels will continue to decline under all three scenarios. Habitats will be reduced by 50% in the next 25 years under the status quo and alluvial well removal scenarios. Curtailing pumping within a 3-mile band around the river extends this threshold somewhat, and about 55% of pools will remain in 40 years under this scenario. Unfortunately, all of these pools are clustered within a 2-kilometer reach of stream, and their depths will be reduced up to 70% of current levels. So even under the most conservative pumping scenario, that of curtailing pumping within a 3-mile band around the river, current fish habitats are not sustainable into the future. So what will it take to maintain current water table levels and fish habitats in the Arikaree into the future? Based on a water balance model of our study area, we predicted that to maintain the current regional and alluvial groundwater stage, and by default fish habitats, pumping from the aquifer would need to be reduced by about 75%. This level of irrigation reduction is likely not realistic from a socioeconomic standpoint. Our research indicates that unless water abstraction is reduced, habitats in the Arikaree Basin will continue to decline and become more fragmented. Throughout this study, we mapped the distribution of flowing, intermittent, and dry segments along the entire river. We found that even during the wettest month of a wet year, a permanent long dry stretch exists in the lower basin, caused by alluvial pumping in this area. As recent as the late 1970s, there was still flow in these downstream reaches, and several of the species that are now extirpated from the basin were collected there. The current situation is that by late summer, wet habitats contract to isolated reaches. Small, isolated fish populations in these core habitats have an increased extinction risk from stochastic environmental events, such as extreme floods or droughts. If populations in these core habitats are extirpated, there is little chance of recolonization from downstream because connectivity with adjacent basins has been cut off. The harsh reality is that fish populations in the Arikaree River will continue to decline into the future. One option for conservation is to seek refugia in other basins and translocate species to maintain genetic diversity. Then, potentially in the future, if conditions improve, these species could be transplanted back to their native habitats in the Arikaree. But the question is, where to put them to weather the storm? We know that mean annual flow in the Arikaree has declined significantly since widespread groundwater withdrawal began in the 1960s. We plotted this relationship for 12 other nearby basins that had gauges. All look like the Arikaree. There is a significant negative trend in stream flow over time for all of these streams. With continued groundwater pumping, managers will be challenged to be able to predict when and where and for how long water will be available to conserve Great Plains fishes. Furthermore, conservation and management will need to take socioeconomic factors into account if any progress is to be made. The bottom line is that we need to figure out ways to keep water in these systems to benefit the persistence of native fishes. We graciously thank Colorado State University, the Colorado Division of Wildlife, and the Colorado Water Resources Research Institute for funding this work, and the Nature Conservancy for providing logistical support.